In this topic we're looking at acids and bases. We'll see what an alkali is and what a salt is, and we will look at the various reactions that are used to make salts. We're going to be making use of chemical equations in this topic, and we'll be taking note of the state symbols in the equations. These are the letters that indicate the physical state of each substance in the equation. Solids, like ice, are denoted with an S in brackets. Liquids, like pure water, with an L, and gases, like steam, with a G. To help us tell pure liquids from solutions, we use AQ to show a substance which has been dissolved in water. Water itself should never be shown as AQ, because water dissolved in water is a pure liquid, so it should be L. When we read a balanced chemical equation, we should also take note of the state symbols. The equation here reads: solid calcium, when added to water, reacts to form a solution of calcium hydroxide and hydrogen gas. This is important because the state symbols are telling us about what we would observe. The hydrogen gas being produced tells us we'd see bubbling from around the solid pieces of calcium. The products consist only of a solution and a gas, so we'd also expect to observe that the calcium will disappear as it reacts with the water. Acids are a family of substances which have similar reactions. The most common laboratory acids are sulfuric, hydrochloric and nitric acid, and you should learn the chemical formula for each of these, as you will be expected to know them. You should also know that acids are likely to be corrosive, and therefore require appropriate safety precautions, such as eye protection and gloves. The most important thing about acids is what makes them members of the acid family. What all acids have in common is that they produce hydrogen ions, H+ ions, when we dissolve them in water. It is these H+ ions that are responsible for the typical reactions of acids. The equation here shows how molecules of hydrogen chloride can be dissolved in water, and when this happens, the molecules split up into hydrogen ions and chloride ions in the solution. It's these hydrogen ions in the solution that make it hydrochloric acid, rather than just a solution of hydrogen chloride. We also need to know about bases. Bases are substances which can neutralise acids, reacting with them to form water. Typical bases include metal oxides and metal hydroxides. Some bases are soluble in water, and these soluble bases are given the special name alkalis. Like acids, alkalis can be corrosive and require the same safety precautions. You'll be expected to know the formulae of common alkalis such as sodium hydroxide, potassium hydroxide or calcium hydroxide. In the same way that acids have one ion in common that makes them all acids, alkalis behave as alkalis because when they are dissolved in water they produce the hydroxide ion OH- in the solution, as shown here for sodium hydroxide dissolving in water. The reactions of alkalis are caused by the OH- ion reacting. One of the clearest examples of this is neutralisation, the reaction by which acids react with alkalis. We've already stated that all acids are acidic because they produce H+ ions, and that all alkalis are alkaline because they produce OH- ions. It's these ions that react together when we react any acid with any alkali. When H+ and OH- react together, the result is H2O, pure water, which is of course neutral, hence the name for this reaction. An important use for the neutralisation reaction is in titrations, which you will meet in the quantitative chemistry topic. Titration works by using an acid or alkali of known concentration to measure the concentration of an alkali or acid which is unknown by measuring the amounts required to achieve a neutral solution. It is important to appreciate the role that water plays in acid behaviour. Remember, acids require H+ ions, and these are produced when the acid molecules are dissolved in water. We can illustrate this through a series of experimental observations using hydrogen chloride molecules. Hydrogen chloride has the formula HCl, the same as hydrochloric acid, but hydrogen chloride is a gas at room temperature. Firstly, we could see what happens when we dissolve some hydrogen chloride in a solvent which isn't water. An organic solvent such as methylbenzene would be suitable. If we do this and test the pH of the solution, we will find that it's neutral. There are no H+ ions present in the solution. Secondly, we could dissolve some hydrogen chloride in water and repeat the pH test. We'd find that the pH of the solution was acidic. The hydrogen chloride has split up and produced H+ ions. We can see when the hydrogen chloride is acting as an acid by reacting it with a reactive metal such as magnesium. First, we need to do a control experiment and show that magnesium does not react with water on an observable timescale. Then we need to put magnesium into our solution of hydrogen chloride in the organic solvent. We will see no reaction because even though hydrogen chloride is present, it can't act as an acid because it can't split up to produce H+ ions. Finally, we should put some magnesium into our solution of hydrogen chloride in water. Immediately we'll see fizzing as the magnesium reacts. Our conclusions are therefore that hydrogen chloride is not acidic and that water is not acidic, but when we dissolve hydrogen chloride in water, the hydrogen chloride and the water interact to produce H+ ions in the solution, and these make the solution into an acid. The same is true of any other acid. Water allows them to produce the H+ ions which are needed for acidic behaviour. Indicators are coloured dyes which change colour in acidic or alkaline conditions, allowing us to determine whether a solution is acidic or alkaline. Since they only have two colours, indicators cannot tell us how acidic or alkaline the solution is. Different indicators have different colours. For example, three of the most commonly used indicators are shown here. Litmus is pink in acidic conditions and blue in alkaline conditions. Methyl orange is red in acidic conditions and yellow in alkaline conditions, while phenolphthalein is colourless in acidic conditions and deep pink in alkaline conditions. If we want to measure how acidic or alkaline a solution is, we make use of the pH scale. This is based on the concentration of H+ ions in the solution, although the numbers get smaller the more acidic the solution is. The pH of an acid can range from 0 up to nearly 7. A pH of 7 is neutral, and then the alkaline solutions range from pH greater than 7 up to 14. We can use a special indicator called universal indicator, which is actually a mixture of indicators with different colour changes, to give us an approximate measure of pH. Universal indicator has a range of colours which correspond to different pH values. Alternatively, we can use pH probes which measure the pH of solutions directly. Now that we understand acids and bases, we can turn our attention to salts. We define a salt as a substance produced when the hydrogen ions in an acid are replaced by metal ions or ammonium ions. This means that there are a huge number of different substances which belong to the family of salts. The substance sodium chloride, which we know as common salt or table salt, is only one example. The names of salts have two parts. The first part is the metal ion or ammonium ion that's replaced the hydrogen ions in the acid. The second part tells us which acid the hydrogen ions were replaced in. For example, sodium chloride is produced by replacing the hydrogen ions with sodium ions. The acid we do it with is hydrochloric acid. All chloride salts start with hydrochloric acid. The salt magnesium sulfate, a common ingredient in bath salts, is made by replacing the hydrogen ions with magnesium ions. The acid we do it with is sulfuric acid. All sulfate salts begin with sulfuric acid. Ammonium nitrate is an important fertilizer. It's made by replacing the hydrogen ions with ammonium ions. The acid we use is nitric acid. All nitrate salts are made from nitric acid. If we look more closely at this process of replacing hydrogen ions with metal ions or ammonium ions, we can see it reflected in the chemical formula of the salt. If we start with hydrochloric acid and split it up into H+ and Cl- ions, then we can replace the H+ with sodium ions, Na+, to give the formula NaCl for sodium chloride. If we start with sulfuric acid and split it up, we get two H+ ions and a sulfate SO42- ion. We can replace the two H plus ions with a magnesium ion, Mg2+, giving us the formula MgSO4 for magnesium sulfate. In the same way, if we start with nitric acid and split it up into H plus and a nitrate NO3- ion, then we can replace the H plus ion with an ammonium ion, which is NH4+, to give the formula NH4NO3 for ammonium nitrate. We should take the opportunity to look closer at chemical formulae for substances such as salts, which are made from ions. If we look at the different ions that the elements can form, we see an important pattern in the periodic table. Elements in group 1 form ions with a 1+ charge. Elements in group 2 form ions with a 2+ charge. Elements in group 3 form ions with a 3+ charge. Elements in group 4 don't typically form ions, so we won't consider these here. The pattern reverses after group 4. Elements in group 5 form ions with a 3- charge. Elements in group 6 form ions with a 2- charge, and elements in group 7 form ions with a 1- charge. Like group 4, the noble gases in group 8 don't form ions. The transition metals are more tricky, and some can have more than one charge. We indicate the charge they have with a number in Roman numerals after the name. So, for example, copper 2 is a copper ion with a 2+ charge. We can also have compound ions, ions containing more than one type of atom chemically bonded together. The only positively charged compound ion we need to know is the ammonium ion, NH4+. There are several common negatively charged compound ions, 3 of which we've met already. The sulfate ion has a 2- charge, and the nitrate ion has a 1- charge, same as the hydroxide ion. The carbonate ion is CO3, 2-, and the phosphate ion, PO4, 3-. The charges on the ions are important, as they're the key to working out the chemical formulae of substances containing these ions. The rules for working out the formula use the 5 steps shown here. We'll apply these rules to some examples. If we want to work out the formula for calcium chloride, we need to recognise that it's made from calcium ions and chloride ions. To do our working out, we write down the formula of each ion, and underneath it the valency of the ion. This is the number part of its charge, ignoring the plus or minus sign. Then we swap the two numbers over, showing that we need 2 Cl- ions for every 1 Ca2+ ion. What we're actually doing here is balancing the amount of positive and negative charge. Finally, we look to see if the numbers can be simplified by dividing them both by the same number, which we can't here. So the formula for calcium chloride is CaCl2. Here's another example. If we want to work out the formula for iron 2 oxide, we write the formula and the valency of the iron 2 ion, and the formula and valency of the oxide ion. Then swap the numbers to see that we need 2 iron 2 ions for 2 oxide ions. And here we can simplify by dividing both numbers by 2. So we need 1 iron 2 ion for each oxide ion, giving the formula FeO. Now we'll try an example that gives a more complicated looking formula, even though the method is the same. We want the formula for aluminium sulfate, so we'll need the aluminium ion with a valency of 3 and the sulfate ion with a valency of 2. Swapping the numbers tells us that we need 2 aluminium ions and 3 sulfate ions, and we can't simplify the numbers any further. Because the sulfate ion is a compound ion and we need more than one of it, we put it in brackets, and the formula reads Al twice, brackets, SO4, close brackets, 3 times. Now it's time to have a go for yourself to practice turning names into chemical formulae. Here are 9 chemical names. Pause the video and work out the formula for each substance using the rules we've covered. Okay, here are the answers. Pause the video to check your answers so that you can see whether you've understood the rules and how to apply them. Soluble salts are made in a variety of different ways using reactions with acids to produce a solution of the salt from which crystals can be obtained. The first method we're going to look at is the direct reaction between an acid and a metal. As you can see from the general equation, when metals react with acids, the products are hydrogen gas and a solution of the salt. From the state symbols, we can tell that the solid metal will disappear when it reacts, and we will expect to see bubbles as the hydrogen is formed. This method does not work well for very unreactive metals such as copper, silver or gold. On the other hand, very reactive metals such as potassium or sodium would react with the acid too violently to be safe. The method we use is carefully planned to help us separate the salt solution we want from the unreacted material. We start by adding the metal gradually to the acid, adding more as the metal reacts and disappears. When we add metal and there is no fizzing, we know that all the acid has been used up in the reaction. At this point, we filter the solution to remove the unreacted metal, leaving us just with a solution of the salt we want to make. We heat the solution in an evaporating dish to remove some of the water until crystals start to form on the sides of the dish, or until about half the water has been evaporated off. And then we allow the solution to cool and leave it to crystallize. Once the crystals have been formed, we can filter again to get rid of any uncrystallized solution and collect our crystals, which can then be dried in a warm oven or between filter papers. If we want to make salts containing the ions of unreactive metals, then rather than using the metal, we can react the solid with an insoluble metal oxide. The products are the salt and water. So we will see the solid metal oxide disappear as it reacts, and we will not see any bubbling. To make salts this way, we add the solid metal oxide gradually to the acid and keep on adding metal oxide so long as it disappears in the reaction. We also usually need to warm the acid to get the reaction to happen at a reasonable rate. When we add metal oxide and it doesn't disappear, we know that all the acid has been used up, so we can filter the salt solution to remove the unreacted metal oxide. As before, when we then heat the solution in an evaporating dish, we can remove some of the water, and then allow it to cool and leave for the crystals to form. The crystals can be extracted from any remaining solution by filtering, and then the crystals can be dried. Insoluble metal carbonates react with acids in a very similar way to metal oxides, and can be used in the same way to make salts of unreactive metals. The only difference, as you can see from the equations, is that the products include carbon dioxide as well as the salt and water. So in this case we would see fizzing as well as the metal carbonate disappearing as it reacts. We add the metal carbonate gradually to the acid, continuing to add more so long as it keeps fizzing and disappearing into the solution. When adding more solid carbonate produces no reaction, we can filter the solution to remove the unreacted metal carbonate, and then heat the solution in an evaporating dish to evaporate some of the water before leaving the solution to cool and crystallize. We can then filter again to obtain our crystals and get rid of any uncrystallized solution. Then dry the crystals in a warm oven or between pieces of filter paper. Salts are also produced when acids react with alkalis. The products are water and the soluble salt. From the state symbols we can see that we are reacting two solutions together and getting a solution plus water, so there will be nothing much to observe. No fizzing and no solids disappearing. In fact, it will be difficult to tell when we've added the right amount of acid or alkali to exactly neutralise the solution. This method is useful for making salts of very reactive metals, such as sodium or potassium salts. We start with the alkali and gradually add the acid to it. Since we can't see when the reaction is complete, we have to take samples frequently and test them to see if they're neutral. This can be done by dipping a glass rod into the solution and placing a drop onto a piece of universal indicator paper, or by using a pH probe. When we've added exactly the right amount of acid to neutralise the alkali, we stop. There's no need to filter the solution because there are no solid reactants or products. We then heat the solution in an evaporating dish as before to remove some of the water, then cool the solution and leave for crystals to form. The crystals are removed from the remaining solution by filtering and then dried. Ammonium salts are produced by this method because when we dissolve ammonia in water, it forms a solution of ammonium hydroxide, which is an alkali. We can use this solution to react with an acid, just like any metal hydroxide solution. When we do so, we will obtain an ammonium salt of the acid, plus water. Ammonium salts are important, especially ammonium sulfate and ammonium nitrate, which are fertilizers rich in the nitrogen that plants need. Our methods so far have been designed to produce solutions of salts from which we can then obtain the solid crystals by evaporating the water. That's fine so long as we want to make soluble salts, but if we use these methods to make salts which are insoluble, then we will struggle to separate the solid salt we've made from any unreacted substances which are also solids. Instead, we form a precipitate of the salt we want. A precipitate is a solid formed in a solution. It's easy to separate the solid precipitate from the rest of the solution by filtering. To make an insoluble salt, we react two carefully chosen soluble salts together. The method consists of mixing the two solutions together to form the precipitate, filtering to collect the precipitate and get rid of the unwanted solution, then washing and drying the solid precipitate. Before we can choose which two soluble salts to react together to make our insoluble salt, we need to be able to tell which salts are soluble and which are insoluble. There are some simple rules which we can use to help us, although they're not perfect or completely comprehensive. All sodium, potassium and ammonium salts are soluble. All nitrate salts are soluble. In fact, we only need these two rules in order to help us choose our reactants for making insoluble salts. The remaining rules help us more generally to predict what will be soluble and gives us some important exceptions. While most chlorides are soluble, an important exception is silver chloride, which is insoluble. While most sulfates are soluble, calcium, lead and barium sulfate are three insoluble ones. Carbonates are insoluble, except those that our first rule says will be soluble. Now we can use these rules to choose our two soluble salts to make an insoluble salt from, and to decide which of our products is going to be insoluble and form a precipitate. We start with the name of the insoluble salt we want to make. In this example, we want to make lead sulfate. We need one soluble salt which will provide the ions for the first part of the name, and one soluble salt which will provide the ions for the second part of the name. One of our soluble salts has to provide the lead ions, so we look at our solubility rules and note that all nitrates are soluble, so we choose lead nitrate as our first soluble salt. The other soluble salt has to provide the sulfate ions, so we use our solubility rules to choose any soluble sulfate, such as sodium sulfate. Now we mix those two solutions together, and the lead and the sulfate ions react and produce the precipitate of lead sulfate we wanted to make. The sodium ions from the sodium sulfate and the nitrate ions from the lead nitrate remain in the solution. The chemical equation looks like this. You can picture it as a kind of partner swapping process. If we apply our solubility rules to the products, it's clear that the sodium nitrate will be soluble, so we can remove this from the insoluble lead nitrate by filtering and keeping the solid in the filter paper. It's important to appreciate that we can make the same insoluble salt by various different combinations of soluble salts. There are no single right answers. We could, for example, have reacted lead nitrate and potassium sulfate with exactly the same results. To finish off this topic, think which two solutions of soluble salts you might choose to mix together in order to make silver bromide. There are quite a few possible combinations that would work.